Hi there, my name is Eric Siebert. Welcome to this session on a deep dive on virtualization. A little bit about me. I have about 5 years experience working with VMware technology. I'm a vExpert 2009 and 2010, speaker this year and back in 2008. Author of 2 books on VI3 and vSphere, frequent writer for TechTarget, and manage the vSphereland.com website. So the goal of the session is, you may understand virtualization and use it every day, but do you really understand how everything works behind the scenes? So we're going to cover that in detail on how all the various components of virtualization work, kind of technical deep dives on all that stuff. We'll basically provide a better understanding of some of the more complex features also of vSphere, so you can better understand them and use them more effectively. So here's the agenda. We're going to cover the basic principles and technology behind virtualization, anatomy of ESX and ESXi, anatomy of a virtual machine. We're going to cover some of the virtualization features that require specific server hardware. We're going to cover how the advanced features in virtualization work, and those features include VMDirectPath, dynamic voltage and frequency scaling, VMCI, fault tolerance, and vMotion storage vMotion. We'll start with the principles of virtualization. We're going to cover a couple of the key components that make up the hypervisor, or make up VMware and vSphere. It includes the hypervisor, the virtual machine monitor, rings, the CPU scheduler, and memory virtualization. So this is basically the definition of a hypervisor, what a hypervisor actually is. It's basically just a program that allows multiple operating systems to share a single hardware host, and each operating system appears to have the host processor, memory, and other resources all to itself. However, the hypervisor is actually controlling the processor and resources, allocating what is needed to each operating system in VM to make sure that the guest operating systems cannot disrupt each other. So there's 2 types of hypervisors. There's the bare metal, which is also referred to as type 1, and that is like ESX and ESXi. And then there's also the hosted hypervisor, which includes workstation, player, server, and that those require an operating system under them, whereas the bare metal ones actually installed directly on hardware. And with the hosted, you have to go through the operating system layer, and that controls access to all the hardware. In ESX and ESXi, the hypervisor is also known as the VM kernel. That's basically the VMware's name for it. The VM kernel is considered a microkernel and has 3 outside interfaces. A microkernel is basically the bare minimum of code that's needed to kind of create an operating system. The outside interfaces that basically allow all the kind of direct access to the VM kernel are hardware, the guest operating system or the guest VMs, and the management OS, which is a service console in ESX, and just the management console in ESXi. The VM kernel directly handles memory and CPU access to all the other devices in a host, like the I/O controllers and that, uses modules or drivers that are specifically adapted to work with the VM kernel. Those modules basically dictate the hardware that can be used with ESX and ESXi, and that's what actually makes up the hardware compatibility guide that VMware publishes for what hardware can be used with ESX and ESXi. There's those drivers are basically just special drivers, kind of like a Windows driver that install inside the VM kernel, and basically they're tested and developed for the hardware that's it's going to be run on to make sure that they're safe and won't crash the hypervisor. The VM kernel does not run VMs directly. That's the virtual machine monitor's job. I'll talk about that in a minute. And in vSphere, the VM kernel is now 64-bit, and VI3 it was a 32-bit application that was they moved it to 64-bit, so you can still run both 64 and 32-bit VMs. We'll talk about that a little bit later too. Here's the other component, or part of the hypervisor, which is called the virtual machine monitor, and the definition of that is a process that runs in the VM kernel, which virtualizes the guest OS instructions and manages memory. The virtual machine monitor passes storage and network I/O requests to the VM kernel, and passes all other requests to the VMX process, which is another kind of little module that runs inside the hypervisor. There's a virtual machine monitor for each virtual CPU assigned to a virtual machine. So if you go into like an ESX service console and run ESX tops or some other program that will show you all the what all the processes are running, you'll see a VMM process for every single virtual CPU for a running VM inside of there. So the virtual machine monitor partitions and shares host resources, including CPU, memory, timers, and I/O devices. It basically decouples the VM from the VM kernel, so the VMs cannot access the VM kernel directly. They actually go through the virtual machine monitor, and that handles all the requests to the VM kernel. The virtual machine monitor is responsible for hardware abstraction and simulating hardware to the guest. So the VMM is basically what is creating that virtual hardware that the guest OS is seeing, and it doesn't actually see the physical hardware of the host. VMware tools includes enhanced drivers optimized for that simulated hardware that the virtual machine monitor is creating. That's why it's always important to load VMware tools, because it has a specific drivers for the hardware that is emulated by the virtual machine monitor inside the VMware tools for each OS. The virtual machine monitor chooses the execution mode for the VM, and the execution mode there's a couple types of execution mode. Basically, what that is how it handles the access to the CPUs. There's one called binary translation, and we'll talk about this. This kind of ties into rings. What the execution mode is like binary translation is the virtual machine monitor is actually running in a ring 0, and it's basically fooling the OS that's running on the VM into thinking it's running in ring 0. There's also another mode called hardware-assisted virtualization, and we'll get into that more with the ring stuff, but basically that is moving the virtual machine monitor down to a lower ring level and allowing the guest operating system to actually run in ring 0. And whatever mode it's choosing, there's also some memory modes, software and hardware MMU. Whatever mode is chosen is called the monitor mode, and the mode that is chosen is often based on what operating system, whether it's Windows or a certain version of Windows, and the 32-bit, if it's 32-bit or 64-bit. So rings are basically a range of protection levels that's basically where code can execute. There's a number of rings, and we'll do a graphic of that in a minute, but ring 0 has the highest level of privilege and is where the operating system kernel normally runs for a traditional operating system. Code executing in ring 0 is said to be running in system space, kernel mode, or supervisor mode. All other code, such as applications running on the operating system, operate in less privileged rings, typically ring 3. And in between those rings, there's other rings like ring 1 and ring 2, and things like device drivers and that run in those other rings. Here's just a little graphic of rings. You can see here, ring 0 is the most privileged ring in the middle there, and then up through ring 3, which is the least privileged, where applications typically run. Between those rings, there's special gates, and access from one ring to another all has to go through ring 0, the kernel. It needs to make a request if an application wants to get to a device driver, and that the actual kernel controls all access to the rings. So here's how rings relate in non-virtualized systems and virtualized systems. The little graphic there basically shows on a traditional server, the ring 0 is where the guest OS resides, like Windows or whatever, and the apps all reside in ring 3. In a virtualized system, the virtual machine monitor runs in privilege mode in ring 0, and the guest OS is bumped up to ring 1. The virtual machine monitor, though, is basically fooling the guest OS into thinking it's running in ring 0, though. And then the middle one there is basically without hardware assist. That would be the binary translation method. The next one is the with hardware assist, which basically is the Intel VT or the AMD-V technology that was developed in the CPUs that basically introduced kind of a new ring called ring -1, and that then pushes the virtual machine monitor down to that ring, -1, and allows the guest OS to go back into ring 0. So the virtual machine monitor doesn't actually have to fool the guest anymore into thinking that it's running in ring 0. It actually can reside there normally, and the virtual assist, the hardware assist, basically just sits down there in ring -1 and handles all the access down to the VM kernel. Here, the CPU scheduler, that's responsible. It's basically another component of the hypervisor that's responsible for scheduling VMs, the virtual CPU time on the host physical CPUs. The CPU scheduler in vSphere is improved to provide better performance and scalability. It's improved across all the versions of all the way from the early versions of ESX 2 to 3 and 4. It was a lot stricter in previous versions. for things like co-scheduling, where it's got to schedule if you have a VM with a couple, maybe 4 vCPUs. With the older versions, it had to actually schedule all 4 of those CPUs on physical cores or sockets at the same time. In VI3, they introduced something called relaxed co-scheduling. What that did was allow it to schedule a subset of CPUs on the physical CPUs, and that made it a lot easier to try to find available CPUs for doing the scheduling. Scheduling on the many vCPUs, they typically outnumber the physical CPUs anywhere, depending on how loaded the server is, from 4 to 8 to 1 maybe. It can be real challenging, and the scheduler specifically has been tweaked across all the versions to be as efficient as possible and do that in a manner where it doesn't allow the VMs to, it's basically the hypervisor has to create the illusion to the VM that they have exclusive access to the CPUs. So it can't really allow to slow down. It's got to try to schedule all the VMs kind of evenly across all the CPUs. To do that, it uses a kind of a proportional share-based algorithm that is based on some of the settings that you set for CPUs inside of a VM, things like the shares and the limits and the reservations. And it also uses some other type of techniques to basically be as fair as possible across when scheduling all the CPU time, so that the VMs kind of get equal time, and some VMs don't get all hung up when they need CPU time. It optimizes the placement of virtual CPUs on the different sockets to maximize the overall cache utilization and to improve cache affinity by minimizing the virtual CPU migration. So basically, if a VM is using a particular CPU, that CPU has its own cache, and basically it's sometimes going to try to keep that VM using that CPU because the cache is already there and relevant to that VM. So the CPU scheduler spreads the load across all sockets by default to maximize the aggregate amount of cache available to the running virtual CPUs. It's possible to override that kind of a behavior for VM workloads that share data between CPUs. There's a special VMX parameter for that. Typically, in most cases, you don't want to do that. The CPU scheduler is pretty efficient at what it does, and that it does a really good job of scheduling in that. And in most cases, you don't want to do that, but it does try to spread the load across all the sockets and make the maximum use of all those CPU sockets so it can schedule the VMs efficiently. Okay, memory virtualization. The VM kernel manages all VM memory. The VM memory consists of the allocated memory, so basically what you assign to the VM. If you assign 4 gig of RAM to a VM, that 4 gig is basically allocated in the host memory, plus a small amount of VMM overhead memory, and that's basically the extra memory on top of that 4 gig that it needs to basically handle the virtualization stuff. The VM and physical host memory are divided into 4K blocks or pages. With vSphere, they also introduced something called large page support, which where the actual memory pages are 2 meg pages. Makes it a little bit more difficult to use the TPS, the transparent page sharing, where it actually tries to merge similar blocks of memory together to reduce the amount of physical memory that a host is using. So host TPS is not used with large pages under most normal conditions. There's some settings for actually that where you can kind of tweak that too. So we're going to talk about the anatomy of ESX and ESXi. ESX and ESXi run the exact same VM kernel code. There's no difference between the kernel on one to the other. The main difference between them is the management components. The ESX uses the larger service console model, and ESXi uses the smaller management console model. Both management consoles run as privileged VMs on the host itself, so they're basically just when the ESX host boots up, it's loading these privileged VMs, and this is the management interface into the VM kernel itself. You'll see now it's not a VM that you can actually do things with. You can't really touch it or see it. It doesn't appear in the vSphere client. If you look on with ESX now, they kind of moved the VMDK file for the service console onto the VMFS data store and made it visible, but again, you can't actually see or do anything with it. Bit of trivia, ESX, when the development code, when it was introduced back in 2001, was Elastic SkyX, which is also the name of the band you'll see tonight at the VMworld party. The ESX Service Console runs a modified Red Hat Linux operating system. The kernel version for vSphere, the current version is 2.6.28. The ESXi management console runs a BusyBox application inside of a POSIX environment. What POSIX is basically, it stands for Portable Operating System Interface for Unix. It's a set of API, shell, and utility standards for Unix variants, and it basically allows you to create a very small portable operating system, which ESXi uses to run the other things on top of it. BusyBox is a single binary that has many applications packaged inside of it. So instead of having an executable for every little application that you're running inside of that POSIX environment, it's all compiled into one big kind of executable, and everything is executed through that BusyBox app. Okay, this is kind of how ESXi is made up. ESXi is available as embedded and installable. If you took that installable and put it on a flash drive and put that flash drive inside of like a Windows server and looked and saw what's on that flash drive, you'll actually see the partition layout is there's a 4 megabyte primary partition, and that's the bootloader, which is responsible for booting up the hypervisor. Then you'll see another partition, a 896 extended partition, that's kind of partitioned up into 4 logical disks. The first disk is a 250 meg logical disk that contains the core hypervisor code, so the VM kernel, which is packaged into several files. They're TGZ files that are total up to about 60 meg in size, so the VM kernel itself is actually very small. There's also server manufacturer customizations that are also stored there for some of the SIM stuff. They store their stuff there also in the OEM.tgz. The second partition is basically kind of a clone of the first partition, and whenever you patch or update ESXi, what it does is take everything from that first partition, copy it to the second partition, and that's your backup. So if you have to fall back, there's an option when you boot up ESXi to actually roll back to the previous version. And that's where it's stored. So it only stores one copy when you actually update. So it's always the current version is in partition 1, the previous version is in partition 2, and it's just basically just an identical copy of the first one. Third partition is a 110 megabyte logical disk that is initially empty, but it can be used for to hold diagnostic core dumps. And the fourth partition is a 286 megabyte logical disk that contains things like VMware tools, the ISO files, vSphere client installer, which actually is not packaged anymore with the 4.1 version, and other tools and drivers and runtime storage. This is basically kind of a visual if you've popped a ESXi flash drive into a Windows server to kind of browse the partitions. You see on the one side, you'll see basically the primary partition, the small one, and the extended partition with the 4 logical disks inside of that. And on the other side, you can kind of see an expanded view of what's actually on those partitions. With the extended partition, the main one there, you can kind of see all the little TGZ files that make up the VM kernel itself. And then on the other disks, you can see some of the miscellaneous files and things like that. Now we're going to cover the anatomy of a virtual machine itself. The definition of a virtual machine is a representation of a physical machine by software that has its own set of virtual hardware upon which an operating system and applications can be loaded. With virtualization, each VM is provided with consistent virtual hardware regardless of the underlying physical hardware that the host server is running. So again, the virtual machine monitor is basically simulating or giving the VM the hardware that's actually seeing, and then it handles from the VM kernel, all the physical server. That's where all the actual drivers are for the actual physical hardware of that host. So virtual hardware of VM exists in the host memory. It's not actual real hardware. And the VM sees the same hardware regardless of the underlying host hardware. VM is encapsulated into a single large virtual disk file. So if you browse a partition where all the VMs are stored, you'll see that large disk. And we'll talk about those more in detail in a minute. A VM consists of a number of files that are located in its home directory on whatever data store that the VM resides on that is accessible by the host. When the VM is powered on, the host mounts the VM's virtual disk, and it provides the VM with the virtual hardware in the host memory. And there's a slight bit of overhead of memory on a host for each running VM, which I talked about earlier. That's that little extra overhead memory, which you can actually see in the vSphere client. When you click on a VM, it shows you the amount of overhead memory that a VM's using for all the virtualization stuff that goes on. So here's kind of the files that make up a VM. There's a variety of files, and these files will all, if you browse again the VM's directory, you'll see either some or all of these files based on the state of the VM, and if you have things like suspended VMs or snapshots in that. And we're going to talk now a little bit more in detail about each of these files. Here's kind of if you actually browse a data store on a host and look in the VM's home directory, you'll see all the files listed there. Again, you're only going to see based on if the VM is powered on or off and things like that in its state. Things like the vswap file won't be present if the VM's powered off. Snapshots won't be present until you actually take a snapshot. But here's all the files. One thing to note is with the when you're browsing through the vSphere client data store browser, the virtual disk file, the VMDK file, actually appears as one file when actually it's two files in that, but the data store browser only shows it as one, and we'll talk about those files in detail in a minute. So here's some of the files. The VMSN file is used with snapshots to store the state of a VM when you actually take a snapshot. A separate file is created for every snapshot that is created on a VM, and it's automatically deleted when the snapshot is deleted. This file size will vary based on whether or not you choose to include the VM's memory state with your snapshot. So if you actually say, when you take the snapshot, I want to include the VM's memory, this file will be about the size of the memory itself, plus a little bit over that for some other data that's stored in there. The VMSD file is used with snapshots to store metadata information. It's basically a text file that basically stores information about the snapshot itself. It's initially a small file, 0 bytes in size, and it's populated with information as you take snapshots. It's always there. It's never deleted. Even if you don't have snapshots, that file will still reside there. There will only be one of these files, regardless of the number of snapshots, because it writes its information for every snapshot inside of this file. The VMSS file, it's used when VMs are suspended, so kind of preserve the memory contents of the VM so it can start up again where it left off. So what it does is dumps the whole the memory of that VM into this file, and it's kind of almost like a virtual memory file. It'll be basically the same size, again, just like the snapshot. If you create the VMSN file, it'll be about the same size of the amount of memory that's assigned to the VM. Even empty memory is written to this file, so if the VM is only using, maybe it's assigned 1 gig, it's only using 200 meg of RAM, it writes every single byte to this file. When the VM is brought out of a suspend state, the contents of this file are written back into the physical memory of the host server for the VM, and this file is automatically deleted when a VM is powered off. If you reboot that VM, it won't actually delete the file until you actually physically power the VM off and then back on. If you delete this file, if you happen or somebody deletes this file, it's no big deal. The VM basically will just kind of boot normally instead of booting from that suspended state. The vswap file. This is created when you power VM on, and what it is allows for it's used when a host is overcommitted memory-wise. Once the host runs out of physical host memory, it uses this file to store memory information for that VM. The size of this file is determined by the amount of memory assigned to a VM minus any memory reservations that a VM may have set on it. So if I assign 4 gig of RAM to a VM, normally a 4 gigabyte vswap file will be created on the data store that the VM resides on. Now if I set a memory reservation, if I set a 1 gig memory reservation on that VM, that basically guarantees that VM has the amount of that host memory locked up, so it's not going to need that in the vswap file. So the vswap file will actually be smaller. It'll only be 3 gig because it'll only need 3 gig if the host eventually gets overcommitted and it needs to go to the vswap file for additional memory. It's always created for VMs, but it's only used if a host exhausts all of its physical memory, so it doesn't actually start using this file. Obviously, it's slower than physical memory, so it won't start using this file until the host runs out of physical memory. Then it starts using the vswap file. Typically not a situation you want to get into because it's a lot slower than the physical memory of the host. These files can take up a large amount of disk space on your data stores, so ensure that you have adequate space available, as VM will not power on if there's not enough space on the data store to create this file. Also, you can specify alternate locations for these files, so if you actually don't even want a file to be created and you want to guarantee the VM has all the host memory that's assigned to it, you can set the memory reservation to, if it's a 4 gig VM, you assign a memory reservation of 4 gig, this file will be created, it'll be 0 bytes, and it won't take up any room on your data stores. You can also specify alternate locations if you don't want these residing on your expensive SanDisk. You want to put them on a local storage or maybe some cheaper storage tier. There's some settings inside the cluster settings and the VM settings where you can actually specify that these files be created somewhere else. They're deleted when a VM is power off or suspended, doesn't need it anymore, and they're recreated on the fly again once the VM is powered back on. As I mentioned before, you can store them on alternate data stores. Some other miscellaneous files. The NVRAM file, it contains the Phoenix BIOS that is used as part of the boot process of the virtual machine. Small little file, it's a binary file. You can actually go in there and look at it and edit it and that. But it basically just like a traditional server has its own BIOS. It's a chip inside of the server itself. This is all packaged into this small file, and it's leveraged when the VM boots up. If you delete this file, it's no big deal. It creates it on the fly again once the VM is booted again. The VMX file is a configuration file that contains all the hardware settings of the VM, basically just a text file. And anytime you make changes in the vSphere client to a VM settings, all that information is stored inside of this file. It contains things like the virtual hardware, what type of virtual hardware is in the VM, specific advanced settings for the VM, and other types of basically information that's relevant to that VM. You can edit this file directly. Typically, it's not recommended, but you can go in there and edit it and make your own changes in there if you want to. The log files, they're used to log information about the VM, and they're often used for troubleshooting purposes. If you want something's going on with your VM, you can look in these log files to kind of see what's going on. It'll log all the information in there. The VMware.log is always a current log file. Then it creates older, other additional log files that have, you'll see a number appended to the end of it, -2, -3, and it'll keep incrementing up. Currently, I think it only retains 6 of those older log files. There's some advanced settings you can set actually to control the size and how many of these log files that are retained. And the VMXF file is basically a supplemental configuration file. You'll see it in there, but it's not actually used with ESX. It's retained for compatibility purposes with Workstation that uses that file. Okay, the virtual disk files, the VMDK files themselves. All virtual disks are made up of 2 files, like I mentioned before. There's the large data file that's equal in size to however big that virtual disk is, unless you're using thin disks. And there's also a small text descriptor file that basically contains information about the geometry of that virtual disk, what basically things like sectors and heads and stuff like that, and what makes it up. The descriptor file also contains a pointer to the large data file. So basically, those two are linked together to each other. So if you look inside the descriptor file, you'll see the pointer, the path information to the data file that's accompanied, that's part of that descriptor file. And like I said, it stores things like the disk adapter type, cylinders and heads and sectors, all the kind of basic characteristics that'll make up that virtual disk. In most cases, the files will have the same name. So if you browse the directory of a VM, you'll see it'll be for example here, my VM1.vmdk will be the one file, and then it adds a -flat to the other file, and basically the prefix of that will basically usually typically have the same name unless you do some renaming of that. You can match the descriptor file to the data file by checking the extent descriptor field in this file to see which -flat, -rdm, or -delta file is linked to it. So you can just look in there and it'll tell you the exact file name of the data file that it's linked to. There's 4 virtual disk file types. Those are the flat.vmdk, which is a normal, traditional, we'll talk about these all in detail, virtual disk. There's a delta.vmdk file, which is used for snapshots. There's a rdm.vmdk file, which is used for raw device mappings. And then there's a new in vSphere, there's a ctk.vmdk file, which is used for the new change block tracking feature in vSphere. So here's the flat VMDK file, the normal traditional virtual disk that you use with all your VMs. Again, it's basically just a large virtual disk data file that is created when you add a virtual hard drive to your VM that is not a RDM. When using SICDIS, this file will be approximately the same size as what you specify when you create your virtual disk. With SYNDIS, they start small, and then they'll grow out as data is written to them inside the operating system. And this little graphic there that kind of shows the relationship between the virtual disk, how it is made up of the 2 files, and kind of the file names there. Okay, the delta file. This is only used when snapshots are created for a virtual machine. So basically, when a snapshot is created, all writes to the original flat file halt. It doesn't write to that file anymore. That disk becomes read-only. And then all the changes, any additional writes that would normally occur to the flat file, are written to this delta file instead. And it initially starts out as 16 meg in size, and it'll grow in 16 meg increments as changes are made to the VM's virtual hard disk. Because these files are a bitmap of the changes made to a virtual disk, a single Delta file cannot exceed the size of a flat file. So your snapshot, a single snapshot, can never grow more than the virtual disk because, again, it's just an exact copy of what blocks have changed in the original. If a block changes more than once, it's still only updated in that same spot. It's not that's why it doesn't expand larger. A Delta file will be created for each snapshot you create for a VM, and the file names will be incremented numerically. So if you, again, browse the directory of the VM, you'll see a 000-delta VMDK, 02.delta VMDK for each snapshot. As I mentioned, these files are automatically deleted when the VM snapshot is deleted, and they're merged back into the original flat file. So when you go to delete all snapshots, what it does is take all the data from that Delta file and starts writing all those blocks back to the original file. Once it completes that, the original file becomes read-write again, and it deletes all the Delta files that exist. Here's the RDM VMDK file. This is a mapping file for the RDM that manages mapping data for the RDM devices. What a RDM is, a raw device mapping where you're actually assigning maybe a LUN on your SAN directly to a VM instead of creating a virtual disk for it. A mapping file is presented to the ESX host as an ordinary disk file available for the usual file system operations. To the VM, the storage virtualization layer presents the mapped device as a virtual SCSI device. So the VM basically has its own disk that's dedicated to it that it can control and use. The metadata is stored in the mapping file, and that includes the locking state and location of the map device for name resolution. If you do a directory listing, you'll see these files will appear to be taking up the same amount of disk space on the VMFS volumes as the actual size of the LUN that is mapped, but in reality, it's just a small little text file. If you actually go open it up and edit it, it's not actually, it's just appearing to be that large. But if you actually go into the VM's home directory and look through other utilities, you actually see that it's a lot smaller. And one of these files is created for each RDM that is created on a VM. When you create an RDM, you can choose between two modes that it can operate in. There's the virtual compatibility mode, and that virtualizes the map device and is mostly transparent to the guest operating system. So basically, it really doesn't see it as a true virtual disk like a physical server was that can directly access and send like SCSI commands directly to the device. And there's also physical compatibility mode, which provides a minimal SCSI virtualization of the map device. And the VM kernel passes most SCSI commands directly to the device, which allows for a closer integration between the VM and LUN. Typically, you want to run in virtual compatibility mode because the physical has some limitations. You can't do things like snapshots and that. But the physical mode, in some cases, if you have an application or something running inside the VM that does need to pass SCSI commands directly to that LUN, you can run it in physical mode as well. Okay, the ctk.vmdk file, this is new in vSphere. It's used by the change block tracking feature of the VM kernel. What change block tracking is basically the VM kernel now has the ability to track all the blocks that change on a VM, all the disk blocks that have changed over a period of time. This is beneficial to things like backup applications. So typically before, when a backup application had to go through and figure out if it's doing an incremental backup, what blocks have changed since the last backup, well, it had to go and calculate that on its own. Now that it can simply query the VM kernel and say, hey, tell me what's changed, and the change block tracking feature will say, oh, here you go, these blocks have what's changed. So it's a much quicker operation. It happens almost instantly. It says, here's the blocks, and the backup application knows it just needs to back up these blocks. And it's incremental backups are a lot quicker now for when using change block tracking. The size of this file is fixed, and it does not grow beyond the initial size unless you increase the size of a virtual disk. The size of this file will vary based on the size of a virtual disk, which is approximately, these files are about half a meg for every 10 gig of virtual disk space. So they don't grow as blocks that are actually changed. They're basically just text information in there that just kind of lists what blocks have changed. Inside this file, the state of each block is stored for tracking purposes using sequence numbers that can tell applications if a block has changed or not. And one of these files will exist for each virtual disk that change block tracking is enabled on. So if you have multiple disks, you'll see multiple of these files there. Okay, now we're going to cover some of the server hardware features that require, the virtualization features that require specific server hardware. vSphere is now 64-bit. VM kernel, as I mentioned, is compiled as a 64-bit module, so you cannot run it or even install it on 32-bit hardware. Intel VT, or AMD-V, which is the hardware-assisted virtualization features, are now, they are kind of required. You can actually get away with not using them as long as you have 64-bit hardware, but you can't run 64-bit VMs on them that require those other features. VMDirectPath, that's a new feature that allows a VM to directly access hardware, and we'll talk about that in a little bit more in detail. That requires some specific features, Intel VT-D or AMD IO-MMU. DPM, the technology that allows you to power off and on hosts as needed based on load. That requires NICs with wake on LAN technology. That's not actually the preferred method of using DPM, but it does work. And then the preferred method is server IPMI or HP ILO. It needs those features to be able to power hosts on and off as needed based on demand. Dynamic voltage and frequency scaling, which we'll talk about more in detail also. It requires an Intel Enhanced Speed Step or AMD Enhanced Power Now. Fault tolerance is very, very picky about what CPUs you can use. It requires basically late model, newer model in the Intel family, Core 2 and a Core i7, and AMD's third generation Opteron families. vMotion requires similar CPU families. You still cannot, no cross-vendor, can't go Intel to AMD. Enhanced vMotion compatibility requires Intel's Flex migration or AMD's AMD-V extended migration. So now we're going to talk about some of the features in vSphere in detail. VMDirectPath allows the VM to bypass the virtualization layer and directly access I/O adapters on the host. Provides better throughput and reduced CPU utilization. It's used, basically for VMs that have very high storage or network I/O requirements. So things like if you have a busy Exchange server and you want to dedicate a network or storage adapter to that VM, VMDirectPath gives it a little bit of extra performance because you're not going through the virtualization layer anymore to get to that I/O device. Relies on the relatively new chipset technology. From Intel, it's VT-D. From AMD, it's IO-MMU. The Intel VT-D has been out for a while, and you can get it on most some of the older, like the G6 HP servers and older. The AMD IO-MMU, they were late to bringing that. It's actually, I think it's out now. It's with like the ProLiant G7s and that. So you need that technology, and I'll show you in a minute how you can tell if your server has it or not to be able to use this feature. So VMs normally do not know physical host memory addresses. The VM kernel traps all the I/O operations that happen from that VM and applies translations to them from the virtual memory addresses that the VM sees. VMDirectPath allows for the remapping of host I/O direct memory access DMA transfers and device-generated interrupts. They uses a special pass-through driver that intercepts all communication between the guest VM device and the hardware device. The pass-through driver performs the translation between the guest virtual address spaces and the actual physical address spaces of the hardware. And the pass-through drivers are specific to each vendor, the hardware devices. And here's kind of a graphic of how that all works. You'll see on the one side, with normal I/O virtualization, inside the VM, it's running a virtual device driver specific to the virtual hardware that the virtual machine monitor is presenting to that VM. So it's not actually running the specific driver that's underlying for the underlying physical host hardware. And that driver basically communicates with the VMM, the virtual device emulation. And inside the VM kernel itself, it has the actual device driver for the physical hardware that's underlying on that physical host. When you get into VMDirectPath I/O virtualization, you're actually running the actual device driver inside of the VM, and that VM can then talk directly to the underlying host hardware. When it returns the I/O path on the return trip, it actually goes through that DMA remapping hardware that I talked about that's built into the VT-D and AMD IO-MMU through a buffer and then back to the application. VMDirectPath, while intended for storage and network adapters, it'll work with most I/O devices. Basically, when you go in there, it'll present a list of everything that it sees. You can use it with the other ones. VMware only recommends that you actually use it for the ones that are actually approved for use with it, but you can, if you have a USB devices or drives that you want to dedicate to a VM, you can go ahead and assign those. It does work. There's many limitations when using this feature, though. You can't use things like fault tolerance, vMotion, DRS, HA, snapshots, things like that. The reason is because that hardware is specifically tied to that VM, the physical hardware of the host, so that VM can't get moved to another host because it's locked into that hardware that's on that physical host itself. So while you do get a bit of extra speed and performance out of it, it does have a lot of limitations that basically tie it to that host that it's running on. It's intended for high-speed I/O adapters such as a 10 gig Ethernet or 8 gig fiber channel, where you want to get the maximum amount of I/O you can possible out of to that VM. Limited use cases, and instead of using this feature, there's other features that also provide some extra performance. The para-virtualized SCSI adapter is a new disk adapter introduced into vSphere, provides better performance than the traditional LSI logic or bus logic adapters. And for network, the new VMXNet 3 adapter that's also new to vSphere provides better performance than the older VMXNet 2 adapter. Okay, another new feature is called DVS. It's dynamic voltage and frequency scaling. It's another green feature in vSphere. It's designed to save power, help you, save the maximum amount of power you can on your host. Unlike DPM, which actually shuts the host down and moves the VMs to other hosts, DVS works while the host is running, and basically what it does is allow a host to dynamically switch CPU frequencies and voltages based on workload demand. So if the CPU on a host is normally a 4 gigahertz CPU, well, it can scale it down using, it's got states, they're called P states, down to a lower level if the VM demand actually doesn't need that full 4 gigahertz. So basically what it does then is enable the processors to draw less power and create less heat, which results in overall power savings. Uses a new CPU power management technology called Enhanced Speed Step by Intel and Enhanced Power Now by AMD. This is accomplished by an interface that allows the system to change the performance states, which are P states of a CPU. And we'll talk about those more in detail. P states are defined by the fixed operating system frequencies and voltages that allow the CPU to operate at different power levels. Processors can operate in several different P states, with the lowest level be defined as P min. That's the actual lowest scaling down that it can go to. So for a 4 gigahertz processor, P min might be like 1 gigahertz. And then there's P max, which is the upper level, which is basically just the maximum speed that the processor can operate at. The processor P space can be controlled by either the system ROM or by an operating system. If you go into the BIOS of your server, on most modern servers, you'll see in the power section, you can enable this. Typically, it's set to different modes inside the BIOS. There's like a high performance mode, which always operates at P max. There's a low performance mode, which operates at the P minimum. And there's kind of an in-between states. And then there's also like a dynamic setting where the operating system itself can control what P states are based on the load. P states are operational states and are different from C states, which are idle states, where the whole core is shut down. So with a P state, you're actually just lowering the frequency and voltage of a processor. With a C state, you're actually just shutting down the whole core and not allowing anything to access that core. In vSphere, P states are controlled by the VM kernel, which optimizes each CPU's frequency to match demand. Your VM's performance is not going to suffer if you use this. It's dynamically going to change these P states based on if the VM requires it or not. So it's a great benefit to using this feature. It doesn't hurt anything. The VM kernel is smart enough to know when it needs to change these P states to match the demands and workloads of the VMs. In vSphere 4.0, it only used P states. With vSphere 4.1, you can use both P states and C states. If you select the balance policy for this, and it doesn't actually use C states, it uses only P states. But there's a low policy that uses both, so it tries to get the maximum amount of power savings by using both C states, shutting down a whole core, and P states to adjust the frequency and voltage. Your server hardware must support switching processor P states. Like I mentioned, most modern hardware does. It's not a licensed feature, so it's available in all editions of vSphere. You can use it with any edition. There's no way to monitor P states in vSphere. You can't actually monitor it in the, like if you have the HP servers and you go to the HP ILO board, there's a power section in there where you can actually, it'll graph out the P states. You can see a visual graph of how P states are changing over time. And it'll show you exactly for every single processor in that unit what P state it's currently operating in. So that's just eventually VMware may put something inside the vSphere client that allows you to monitor that. But right now you have to go to your hardware to look at it there. To enable it, you select the configuration tab in the vSphere client. Then in the software panel, you select advanced settings. you select power and then change the power.cpu policy from static, which where it doesn't use p-state, to dynamic, where it'll start using them. And that change happens on the fly. As soon as you change it, the p-states will start changing right away if the server requires it based on demand. Here's that setting. If you click on, in the vSphere client, if you click on processors, it'll tell you if you have the technology available to actually use that. So what you'll see here, it says enhanced AMD power now. The Intel one will say the other enhanced speed step. And then below that, it says the power management policy. High performance here, you can see, is basically where it's not going to change P states. It's always going to operate at the highest Pmax state. And then below that, you can see this is the setting where you actually change it in the advanced settings, where you can change from static to dynamic to enable it. Okay, another new feature is called VMCI. It stands for Virtual Machine Communication Interface. It's a new interface that introduced into vSphere that allows two virtual machines on the same host to communicate with each other via a special high-speed interface. This interface operates independently of the guest networking stack, so communication rate is close to that of the memory bus of the host server. It's almost 20 times as fast as a 1 gigabit speed network connection, and is not subject to the typical latency that is inherent in most networks. The speed is actually based on, there's a calculation for it. We can actually calculate it out. It's typically around maybe 20 to 30 gigabit compared to the 1 gigabit network speed. It's all based on how fast, what type of memory you're running in that host, and how fast that memory is. It's very beneficial to multi-tier applications that have different components running on different servers, such as web application database servers. So if you have a multi-tier app and those apps are talking back and forth to each other a lot, and typically that's over the network, you can use VMCI instead, and that communication rate between them will be at a much higher rate. What it uses is things called VMCI sockets. They're similar to other socket types like Windows sockets. It's a special kind of socket that VMware created that support both connection-oriented stream sockets like TCP and connectionless datagram sockets like UDP. It's only intended for applications that are designed to communicate via VMCI instead of using the regular traditional network. Currently, there is not a whole lot of applications that are actually designed to use this feature, but I think you'll see there'll be more of them that are coming and adapting their apps to actually take advantage of this feature. VMware also provides a special VMCI sockets API that allows developers to adapt their applications to the VMCI interface. They actually have a whole bunch of coding examples. It's not too difficult. They give you examples of exactly how you can change your apps to use traditional network sockets to use these VMCI sockets instead. If your app does not support it, it's not going to work. You can turn it on, nothing's going to happen. And to turn it on is basically just a check mark and inside the VM settings where you can enable this feature. But like I said, if your app doesn't support this, then it's pretty much worthless if you turn it on. Here's kind of a visual of how it works. You'll see here that there's a special library that the application has to leverage where it knows to use VMCI sockets. There's a driver that is at the kernel level that actually installs inside of the VM itself as part of VMware tools. The virtual hardware of the VMCI device, it's a special adapter that's inside the VM. If you go edit the VM settings, you'll see it in there. You can't delete it. It's always there. And then inside the VM kernel itself, there's a VMCI core driver inside of that handles all the communication path between the VMs. So like I said, the drivers for VMCI are built into VMware tools. If you install VMware tools, that driver will automatically be there. Like I mentioned, there's currently not much vendor support for this feature, despite its clear advantages. That'll probably improve as more vendors get on board with it. When you're using this feature, vMotion and fault tolerance are not supported. They work, but what happens is when a VM moves from one host to another host, all the VMCI sockets that are open currently get killed, and once they're on the new host, they'll reopen up. That's why it's kind of critical to keep those VMs on the same host, so they're always going through that VMCI layer to talk to each other. If you're using things like DRS, you can set a rule to keep the VMs always together, so no matter if they do move, they're always on the same host together so they can use VMCI. The VMCI adapter is essentially a special NIC that is assigned, if you look in the configuration file of the VM, it's assigned a PCI slot number as well as a unique ID, which is equivalent to a MAC address. So you'll see in there there's a special ID that's assigned for every VMCI adapter that's unique that it uses to communicate and identify each adapter from each VM. The The development guide, like I mentioned, allows you to modify your own applications, use VMCI. It's pretty handy. It gives you code examples and everything else, instructions on how to, if you have your own homegrown apps that where maybe you want to take advantage of this feature, you can go ahead and modify them to use it. Hey, fault tolerance. Fault tolerance is a new feature in vSphere that takes the HA feature to the next level by providing a continuous availability for a VM in case of a host failure. Fault tolerance works by keeping a secondary copy of VM running on another host. In case of a host failure, the secondary VM becomes the primary VM, and a new secondary is spawned somewhere on another functional host. The primary and secondary VMs stay in sync with each other by using a technology called record replay, which works by recording the computer execution on a VM, saving in a special log file, which is replayed on another VM. This technology was first introduced in the VMware Workstation, and they've since migrated to use ESX for the fault tolerance feature. Record replay functionality is built into certain models of Intel and AMD processors, and VMware's official name for it is called vLockstep. That's why fault tolerance is very picky about which hardware, what CPUs it supports, because it relies on this special technology in the CPU itself to do the fault tolerance. The primary and secondary VMs receive the same inputs. Only the primary VM produces output, though, such as disk writes and network transmits. Secondary VM's output is suppressed by the hypervisor, and it's not on the network until it becomes a primary VM. You'll see it on the host, but it's not actually doing anything. It's not communicating with anything. The hypervisor is basically just updating it, and if it ever needs to become a primary VM, then it kind of releases it and becomes a primary. Not everything that happens on the primary VM is copied to the secondary VM. Certain actions and instructions are not relevant to the secondary VM. If it tried to move everything from the primary to the secondary VM, there'd be so much data going back and forth that they would it'd be really hard to keep them in sync. Only non-deterministic events, which include inputs to the VM, like disk reads, received network traffic, keystrokes, mouse clicks, and certain CPU events are actually recorded and replayed on the other side. Inputs are fed to the secondary VM at the same execution point, so the exact state is a primary VM. So if it needs to take over as the primary VM, it's exactly where the primary VM was. They're always kind of connected at the exact same state, so it doesn't even miss a beat when it moves from the primary to the secondary. Here's kind of a graphic of how the record replay works. You can see on the record side, it's only using things like keyboard and mouse input, I/O devices, network input, disk reads, and CPU timer events. It's sending them over a special FT logging network that you configure on your vSwitches, sending it back and forth. Sends all the traffic from the primary to the secondary. Secondary sends back acknowledgments saying it receives the data because it's important for that VM to be exactly in the same state, so that they're always talking back and forth to make sure they're exactly in sync. You can disable, if you want to reduce some of the traffic on this logging network, you can actually turn off the disk read part of it. There's a special setting you can set for fault tolerance that'll not send the disk read traffic over the logging traffic and have the actual secondary VM do disk reads directly to the disk itself. That basically helps it to, if you got a busy connection between them or they're getting out of sync, you could turn that off to reduce the amount of traffic that's happening between the two, the primary and the secondary VM. So information from the primary VM is copied to the secondary VM using the special logging network that's configured on each host server. Information that's sent over the FT logging network between the hosts can be very intensive depending on the operation of the VM. In the event of a hardware failure, there is no interruption of service or data loss, as a secondary VM can always reproduce execution of the primary VM up to its last output. You can use FT and HA together to provide maximum protection if both the primary and the secondary host failed at the same time. HA would restart the VM on another host and then respawn a new secondary on another functional host. It's a great feature, but it has a great deal of requirements and limitations. The biggest one for the hosts are you must have an FT-capable processor, and both hosts must be in the same processor family. It's very particular about the CPU that is required for this. So VMware publishes a knowledge base article that lists all the models that you can use as fault tolerance, but they have to be very, very similar to each other to be able to use the feature. The CPU clock speed is also must be very close to each other because it's constantly, you don't want the secondary VM dragging down the primary VM because it's got to wait, the primary has to wait until the secondary acknowledges all the inputs that are sent over. So that's why the CPU speeds, they must be within 400 megahertz of each other to ensure that the host can stay in sync. what the actual feature of fault tolerance also is, if the secondary is getting too slow and it can't keep up anymore, what the primary is going to do, there's a response time between them that it's always measuring, is basically kill that secondary and say, you're too slow, you're dragging me down. What I'm going to do is start a new secondary on a host that may have more additional, better resources, so they can better stay in sync with each other. The biggest VM limitation is the VM must be a single processor. You can't use vSMP. That's kind of a big showstopper for a lot of people right now that want this for their critical applications that typically require maybe multi-CPUs like Exchange and SQL servers. Eventually, VMware, I know they're working on getting vSMP support for this, so you'll be able to use multiple processors in your VM at some point in the future with this feature, which is a great thing to have. But it's so complicated sending all this stuff back and forth right now. They've only got to the point where it can do that with a single CPU. Multiple CPUs will require a lot more development to figure out how to get all that data back and forth. It only protects against host failures. It doesn't protect against application or other infrastructure failures. It's only designed for if something happens with that host. It's not designed for something happens with that application or inside that OS. If you get a blue screen on one host, you're going to have a blue screen on the other host, and they're exactly in sync with each other. So it's only protecting against something, your infrastructure, with that host, whether it completely crashes or has a problem inside of it. It protects against that. Like I said, it doesn't protect against application failures. If you need an application protection like that, you typically implement a clustering solution instead of this. Features, a lot of features not supported with it: snapshots, NPIV, PV-SCSI adapter, physical RDM, storage vMotion. Because of high overhead and limitations, use FT sparingly. Don't go crazy and try to use it across all your VMs. It does generate a lot of extra overhead on the host and that FT logging network, so try to limit its use to the VMs that only need it, and try not to put too many FT-enabled VMs on a single host. Try to spread them across other hosts. In a split brain scenario, a special lock file is used to prevent the secondary VM from trying to become the primary, resulting in two primary VMs running at the same time. And what that does is both the primary and secondary can see that file. A split brain scenario is when the primary and the secondary hosts, they lose communication with each other, like the network crashed or something. They both think they are isolated now. They don't know the other state of the other one. So the secondary VM is going to want to try to become the primary because they can't see the primary anymore. So what it does is this lock file is, if the primary is actually still up, it's got a lock on this file. The secondary VM can't write to this file, so it knows that the primary VM is still up based on this lock file, and that prevents you from having two primaries running at the same time, which is not a good situation. Backing up FT-enabled VMs can be tricky because many backup applications rely on VM snapshots, and you can't do VM snapshots when using fault tolerance. There's some alternate methods you can use, such as OS backup agents, run the backups inside the VM like you normally do with traditional physical servers. Try cloning, temporarily disabling FT, and store snapshots instead as alternate backup mechanisms. You can enable and disable FT via code, via like PowerShell. So if you do have a backup application, for like running VM backup and you want to back up an FT-enabled VM, what you could do is call a PowerShell script to just temporarily disable FT while you're doing the backup so you can take that snapshot. Once the backup completes, you can do another call back to turn it back on. You can easily enable or disable FT at any time. If you want to do something that is not supported, like a vMotion or a snapshot or hot add of hardware, it's pretty simple just to enable and then re-enable it. You can both enable and disable, and you can completely turn off the feature. If you disable the feature, it's basically just not sending the inputs back and forth anymore. But it does preserve that secondary VM and the configuration and history, so it can easily be re-enabled, and then it'll start sending that data back and forth. Turning it off deletes all that stuff, and if you turn it on back again, it's got to recreate the secondary and all that again. vMotion. We're running out of time here, so I'll kind of just go over this real quick. Most of you know what vMotion is. I'll kind of go instead into the how vMotion works. What happens when we actually do a vMotion is a migration request is made to move the VM from the first host to the second host. The vCenter verifies that the VM is in a stable state on the first host. The vCenter server checks the compatibility of the second host and makes sure that it matches, so it's like all the networking that's configured on the first host is also the same on the second host. The VM is registered on the second host, so that's the first step. It actually registers the VM on the second host. Then the VM state information, including the memory, registers, and network connections, are copied to the second host. And then additional changes are copied to a memory bitmap on the first host. and basically it's going to use that to know what it needs to copy finally before it makes completes the vMotion process. The VM is then QoSed on the first host, and the memory bitmap is copied over the second host. The VM is started on the second host, and then all requests for the VM are now directed over to that second host. Then a final copy of the VM's memory is done from the first host to the second host, and then the VM is finally unregistered from the first host and resumes normal operation on the second host. Enhanced vMotion compatibility, basically a new feature that allows you to create a consistent CPU mask. It'll mask certain features of the CPU so you can do vMotion. A lot of times, vMotion, basically how it works is that it'll present, when you boot an application, it looks at the CPU that's inside of it to see what CPU features it has, and then the application can take advantage of those certain CPU features. If a VM moves from one host to another host, those exact same CPU features need to be on the other host, because if it tries to use them and if they're not there anymore, well, then typically the application will crash or the OS will crash. So EVC basically allows you to mask a lot of those features and basically present a consistent, you kind of pick the features that you want to appear to all the VMs across the board. So if a VM moves from one host to another, you don't have to worry about the CPU features not being missing, and it just gives you a better compatibility between those hosts. Still does not allow for, you can't go from Intel to AMD. You can never do that. You can't never vMotion from one to another, because the CPU features and all the chipsets are completely different. And then all hosts in the cluster must have a hardware live migration support, which is Intel Flex Migration or the AMD-V extended migration, or have a CPU whose baseline features set you tend to enable for that cluster. Host servers must have the following enabled in their BIOS. You must, for AMDs, you have to use AMD-V and no execute, and for Intel VT and execute disable. Storage vMotion, again, most of you know what that is, so I'll kind of just go on to the process of what happens when you do a storage vMotion. First thing that happens is a new VM directory is created on the target data store. The VM data files and virtual disk files are copied to the target directory, so you're moving the VM from one data store to another. ESX host is a self vMotion to the target directory. Then the change block tracking feature kicks in. It keeps track of all the blocks that change while you're doing the copy process, so it's got to know basically what I need to, because the VM is still running, what I need to copy at once the copy process completes. So the VM disk files are copied to the target directory. The disk blocks that have changed before the copy are completed are copied to the target disk file. Source disk files and directory are deleted from the source data store. And that's it, basically, simple vMotion. If you want to learn more about these advanced features, I kind of go into detail. I have a Train Signal Pro Series video I did on that kind of goes into detail of all the how to use these features, how to set them up, configure them, requirements, limitations, and everything else. So thank you for coming.